In this film, we're going to look at some experiments which tell us something about a very important and interesting part of physics: radioactivity. First of all, a way of detecting radioactivity. This battery is connected to two metal plates with a gap between them. That's an insulating sleeve. And here's one of the plates. And this other lead's connected, again through an insulating sleeve, to the other. There's air, of course, between the two plates. One of the leads is connected also to this sensitive galvanometer. This shows no deflection, because the air between the two plates does not conduct electricity, and no current can flow. But suppose we place a sample of a radioactive substance under the plates. A current passes. The invisible radiation coming off from the source is making it possible for charge to pass across the gap between the plates. If we remove the radioactive source, current stops flowing. Replace it, and current flows again. Our radioactive source, it contains a radioactive element called americium-241, is giving off charged particles called alpha particles, some of which are passing up between the plates and causing the effect we've seen. Now see what happens if we place an ordinary thin paper tissue over the radioactive source. It must stop the alpha particles, for the current falls to zero again, and then passes once more when we remove the tissue. Alpha particles are heavy particles which are very easily stopped in their tracks. This is a form of radiation which is not very penetrating. What causes the current to pass? Is it the alpha particles themselves, or is it the effect they have on the air between the plates? Here's a way of finding out. We've got the same radioactive source containing americium-241 and the same arrangement of two plates, but this time we put them in a glass container from which we can pump out all the air. A metal gauze cover will shield us from flying glass if the vessel shatters when it's evacuated. We make the same connections as before. Current passes just as it did before. Will current still pass between the plates if we remove the air from between them? Let's use the vacuum pump to find out. Alpha particles are still streaming off from the radioactive source, but look, the current quickly dies away. Without air present, the radiation does not cause the current to flow. No air, no current. The alpha particles, the radiation, cause a current to flow because they affect the air between the plates, producing charged ions which carry the current. Let the air in again, and a current passes once more. Cutting off a block of solid carbon dioxide to use in a diffusion cloud chamber. This is a device which enables us to see radiation, such as the alpha particles whose effects we watched in the last experiment. Contact with a warmer metal plate causes these strange sounds. We pour on alcohol. A plate with a felt pad on top. More alcohol to soak the pad. A glass cylinder. A lid with another alcohol-soaked pad on its underside. Inside this vessel, we're going to mount a rod which has some radioactive radium-224 at its tip, another source of alpha radiation. Don't worry about the purpose of these electrical connections at the moment. You can find out about them afterwards. A lamp is now switched on. Inside the glass chamber, it gets colder and colder as one passes from top to bottom, because of the solid carbon dioxide underneath. Alcohol vapor sinks slowly downwards from the pad under the lid. The tiny invisible alpha particles streaming off from the needle hit some of the molecules in the chamber and turn them into charged ions. Alcohol condenses, forms liquid droplets on these ions, and so reveals the paths of the alpha particles. We're looking at the tracks of alpha particles shooting off at random in all directions from the radium source. The tracks sink downwards because the liquid droplets fall under gravity. Watch. This is radioactivity in action. For a third experiment, we're going to examine an important feature of radioactive substances. Their radioactivity gradually falls, decays, as time passes. We shall measure one particular radioactive decay. This is a counter, a measuring device based on the same principle we met at the start of the film. Radioactive particles cause a gas inside to become electrically conducting. Each particle causes a click. At the moment, it's measuring background radiation, the natural radiation that's always present from the various materials around us and from cosmic rays. This apparatus will count for us the number of clicks in 1 minute. The number shows up at the top left, there. Coming up to 1 minute. Background count, 14 counts in 1 minute. You can take readings down as the experiment proceeds. This is a neutron source, which we're using to create a radioactive element. The element indium, in the form of a metal foil, has been placed inside. Now, after several hours, it contains a radioactive isotope of indium, which gives off charged particles called beta particles, lighter than alpha particles. Listen. We shall shield the counter from all background radiation using these lead blocks. Then measure the radiation every 15 minutes as the indium decays. We start at 9 o'clock. If you want to do the experiment, make a note of this time. Now let's see how many counts there are in 1 minute. How many beta particles are given off. Here it is, 556 counts per minute. (9:15), 15 minutes later. Now, 478 counts per minute. The radiation is decaying. 9:30. (363 counts per minute. 9:45. 297 beta particles per minute. Ten o'clock. $263. 10:15. There are now only 233 counts in a minute. 10:30. 171 counts. 10:45. 140. 11 o'clock. The counts have now dropped to 130 per minute. Fifteen minutes later. $11:30. Down to 96. Last time but one, 11:45. Only 77 counts. Last reading at 12 o'clock. $62 counts per minute. You can afterwards draw a graph using these readings to show how the radioactivity decays. You plot counts per minute on the vertical axis and time in hours on the horizontal axis. There are the points. And this is what's called the decay curve. All radioactive elements have this kind of decay curve. It's called an exponential curve, although some decay much more slowly than others. The background count we measured is shown by the dotted line, and you can see that the radioactivity of the sample is approaching the background value after only a few hours. This was a short-lived isotope. This is an experimental nuclear reactor at the Harwell Laboratories of the United Kingdom Atomic Energy Authority. One of its uses is to carry out all sorts of tests on the effect of radiation on various materials for the nuclear industry. Inside a reactor, this is a cutaway model, there are fuel elements arranged in such a way that nuclear reactions take place which generate heat. There's also a great deal of radioactivity inside the reactor, so there has to be a lot of shielding around it. There's a 4-inch thickness of lead to stop gamma radiation, and a 6-foot thickness of concrete around that to stop the particles called neutrons from getting out. Here's one of the cans containing nuclear fuel for the reactor, uranium in this case. It's quite safe to handle before it's been used in the reactor, but when it's removed, because the nuclear fuel has been used up, it's a very different matter. They're removing a spent fuel element. It's so dangerously radioactive that it needs this huge container, it looks like a space rocket, to carry it in. This weighs 21 tons and has thick lead and steel shielding, all to carry one of those quite small fuel cans. the very radioactive spent fuel element is taken to a special building where it's going to be stored for a year or so while the radiation decays. It's going to be dropped out through that small circular hole. Into a deep tank of water. There it goes. This depth of water shields the workers above from the gamma radiation. Gamma rays are like X-rays, only they have shorter wavelength and are even more penetrating. Now the ends of the can are sawn off, all by remote control, underwater, leaving the center portion which contains the radioactive spent fuel. The can is now passed through to the storage pond, where it will remain until its radioactivity has greatly decayed and it's no longer so dangerous. Here it comes. It's going to be kept upright at the bottom. All these precautions show one of the difficulties about using nuclear reactors. The waste produced can't just be dumped. It's got to be looked after very carefully, although it can eventually be reprocessed to be used again in the nuclear industry. The invisible gamma rays coming off from all these decaying spent fuel elements are highly dangerous to living things. In fact, the radiation at the bottom of the pond would be absolutely fatal if we were exposed to it. This gives us a use for this decaying nuclear waste. These drums contain surgical instruments which need to be sterilized. They're things like plastic disposable syringes, for example, which would be damaged by heat treatment. They're sealed in plastic bags, then placed in the drums and lowered into the pond. Once the drum's near the spent fuel elements, it's exposed to intense gamma radiation. This kills any bacteria present, so that the instruments become absolutely sterile and can be safely stored inside their plastic bags until they're needed. They mustn't be left too long, however, or the radiation would damage the material the instruments are made of. Gamma radiation can harm plastic. After about 24 hours, the drum is taken out. The contents don't themselves become radioactive, and this is a very good use for gamma radiation. The fact that the label on the drum has turned red, it was yellow, indicates that the drums have had just the right amount of radiation. Radiation can be a dangerous thing. It's important that everyone should understand enough about the subject to be able to judge when it's being used to our advantage. In this film, we're going to look at some experiments which tell us something about a very important and interesting part of physics: radioactivity. First of all, a way of detecting radioactivity. This battery is connected to two metal plates with a gap between them. That's an insulating sleeve. And here's one of the plates. And this other lead's connected, again through an insulating sleeve, to the other. There's air, of course, between the two plates. One of the leads is connected also to this. It must stop the alpha particles, for the current falls to zero again, and then passes once more when we remove the tissue. Alpha particles are heavy particles which are very easily stopped in their tracks. This is a form of radiation which is not very penetrating. What causes the current to pass? Is it the alpha particles themselves, or is it the effect they have on the air between the plates? Here's a way of finding out. We've got the same radioactive source containing americium-241 again. Our radioactive source, it contains a radioactive element called americium-241, is giving off charged particles called alpha particles, some of which are passing up between the plates and causing the effect we've seen. Now see what happens if we place an ordinary thin paper tissue over the radioactive source. Sensitive galvanometer. This shows no deflection, because the air between the two plates does not conduct electricity and no current can flow. But suppose we place a sample of a radioactive substance under the plates. A current passes. The invisible radiation coming off from the source is making it possible for charge to pass across the gap between the plates. If we remove the radioactive source, current stops flowing. Replace it and current flows.